Let's consider the function f, that is x squared minus x minus 2. Now, we're rolling way back into the days of Algebra 1, but I want to make a point here about roots, and perhaps a pattern you've noticed. This function factors as follows. So, because this function factors this way, we have roots at -1 and +2. You may have noticed the following pattern, that roots occur at some number that seems to be related to the coefficients on the first and last terms in the quadratic. Let's try it with a slightly more complicated one, just to convince ourselves that that's still true. 2x squared minus x minus 3. So this factors as follows. And in factoring as follows, there are 2 roots. So at x equals -3/2 or at x equals, +3/2. X equals +3/2 or x equals -1. And you'll notice this, that these roots, something like 3/2, somehow related to the first and last coefficients. -1, a little less obvious here. There's a connection here to these leading and trailing coefficients. And this is where the rational root theorem comes in. The rational root theorem allows us to take an unfactored form of a polynomial function and identify candidates that might possibly be roots that are rational numbers for that function. Now, not every polynomial has all of its roots that are rational, but if they exist, the rational root theorem will help us find them. This is the rational root theorem. It's useful for identifying candidates that might possibly be rational roots of a polynomial. Let's take a look at how the rational root theorem is useful in practice. Show that g of x equals x cubed minus 4x minus 2 has no rational zeros. We're going to use the rational root theorem, which finds us candidates for rational zeros. What we're supposed to do is apply the theorem in this way. So in our case, a sub 0, the constant term is -2, and a sub n, the leading coefficient, is 1. All right, all of the factors of a sub 0, plus and minus 1, plus and minus 2, and all the factors of this term, just plus and minus 1. The rational root theorem says all of the factors of a sub 0 divided by all the factors. So this is actually, there's a bunch of candidate roots in here. So I'm going to start with +1 over +1. That's one candidate root. And that simplifies to either +1 is a possibility or -1 is a possibility. Another candidate, let's call that candidate 1, candidate 2, positive and -2 divided by positive and -1. So the possibilities here, this is just winds up being positive and -2, or is our other possibility. these are candidates to be roots. We actually have to check if they are roots. In my opinion, the easiest way to check if something is a root is to substitute that number into the function, evaluate the function, and see if it comes out to be 0. Let's evaluate the f of 1, f of negative 1, and then also f of 2 and f of negative 2. So as opposed to there being infinitely many possible roots, who knows what they are, we had 4 candidates here to try and a couple options to evaluate. So let's evaluate f of 1, x cubed minus 4x minus 2. It's negative 5. F of 1, not a root of the original function. That's f of negative 1. F of 1 is 1, so that's also not a root. Carry on here. So let's get a big view of this here. What have we discovered? The rational root theorem told us that there were a couple of candidates to be roots to this function. We evaluated all 4 of those candidates. None of them are roots. Therefore, this function has no rational zeros. None of the possible candidates worked out, so therefore, yeah, I just noticed that I switched the function name from G to F. My apologies. Let's do it for the thumbnail. Update this. This function G has no rational roots.